The task in this lecture is relatively straightforward. We're going to do a loop integral. And that's basically the point of this, is to show you the basic techniques of loop integrals, and we'll get back to the more details in the future. But let's do the basics today. So what we're doing is we're doing the scattering process. We have the basic interaction. We added loops that look like this, plus that guy goes up there, those diagrams, and we added a piece that was the delta lambda counter term. We wrote the matrix element minus im is minus 6i lambda renormalization condition 2, which we'll soon just call lambda, plus 1/2 minus 6i lambda squared, and this was I of s plus I of t plus I of u minus 3 I of 0. And just for completeness, the cross-section, which we calculated previously, is 1 over 128 pi squared s, this matrix element squared. So there's our statement. So our task today is to calculate, well, what we need to calculate is I of some momentum minus I of 0. Okay, there's 3 of these here. S was P1 plus P2 squared. T is P1 minus P3 squared. U is P1 minus P4 squared. And so P could be either of those guys. Okay? And so let's call this delta I. So we have to calculate that. And I previously also wrote out what this is. This is integral d4k, 2 pi to the 4th. I of p was 1 over k squared minus m squared plus I epsilon. There's an I over k minus p squared minus m squared plus I epsilon. So that's I of p, and you substitute p1 plus p2, p1 minus p3, etc. And then we're instructed to subtract off I of 0, k squared minus m squared plus I epsilon, I of k squared minus m squared plus I epsilon. Okay, so we subtract off that piece. And it's not too hard to combine these. You put them over a common denominator and combine them. There's a minus sign out in front from the 2 factors of I, and then it turns into integral d4 k over 2 pi to the 4th. Well, putting it over a common denominator has the denominator being k squared minus m squared plus I epsilon, that quantity squared, and 1 factor of k minus p squared minus m squared plus I epsilon. So you put them both over those, you combine the numerators. The numerator turns into 2k dot p minus p squared. Okay, it has to vanish as p goes to 0 because this is defined to vanish in that place. Integral d4k. So at this stage, this is just math. There's nothing, no physics in what we do for the rest of this. We just want to calculate that integral. Now, it's going to be interesting to see just how painful calculating this is. As I said, this is the simplest integral around, and that's why I'm using it as the first example. And it's going to take us a good deal of work. So, here we go. The first step, there's a standard pathway for these integrals. The first step is always what's called Feynman parameterization. Okay, and this is the trick of combining those denominators into a single object. So there's in this particular integral, there's one denominator squared, and the other denominator is the first power, and we want to combine them. Okay. And Feynman parameterization uses this trick. There's various versions of this. You'll see other versions too, but here's the one I'm going to use. 1 over a1, a2, dot, 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 up to an, just any object at all, doesn't matter what they are, is n minus 1 factorial, integral 0 to 1, dz1, dz2, dot, 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 up to dzn, delta of 1 minus z1 minus z2 minus dot, 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 up to zn, over a1z1 plus a2z2 dot, 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 up to an zn to the end. Okay, that's a somewhat obscure integral, but it's a simple direct integral. And what this does is it lets you take the product of the denominators and make it into a sum, raised to the nth power, of course, but that's what it is. Okay, you could also take the same formula and just differentiate with respect to a1, 1 over a1 squared, a2, an is then n factorial, 0 to 1. Well, I have a z1, dz1 now from differentiating. But then the rest is the same. dz2 up to dzn, delta function of 1 minus z1 over the same denominator to the n plus 1. Okay, so those are two basic Feynman parameterization identities. For us, we want the following. For us, we have 1 over a1 squared a2 is the integral 0 to 1 z1 dz1 dz2 delta of 1 minus z1 minus z2 over a1 z1 plus a2 z2 cubed. That's the identity, but it even simplifies. It's the integral 0 to 1. You can do the dz1 integration. Z1 turns into 1 minus z2 dz2 over A1, 1 minus Z2 plus A2, Z2 cubed. Okay, so for us, then this is our identity. We're going to take these energy denominators and write 1 over k squared minus m squared plus I epsilon squared 1 over k minus p squared minus m squared plus I epsilon, and write that as the integral dz. Let's forget the subscript now, it's just dz, 0 to 1, 1 minus z, and this is then k squared minus m squared plus I epsilon, 1 minus z, plus the second factor was z times k squared minus, k minus p squared minus m squared plus I epsilon, that's cubed. This factor here, I'll just call d, that's d cubed. And if you work on it a little bit and take, so you expand this, d turns into k squared minus 2k dot p times z plus z p squared minus m squared plus I epsilon. Okay, so there's the first trick. Trick number 1 is this Feynman parameterization, and now instead of having 3 separate factors in the denominator, we've got 1. The second step is almost always the following. It's almost always complete the square. Okay. Which means that this factor here, it isn't quite the square of something. So I'm going to define L. Here's now L. L is going to be defined as K minus ZP. Okay. Then L squared is K squared minus 2K dot PZ plus Z squared P squared. So the factor there in D is really L squared. So if I can rewrite D is now L squared plus Z 1 minus Z P squared. Okay, that cancels off the Z squared P squared piece. Minus M squared plus I epsilon, which for the rest of this work is going to be defined as L squared minus A squared, just a number now, plus I epsilon. I'll keep that separate. A is then M squared minus Z 1 minus Z P squared. Okay. We'll use use integral d4L is equal to integral d4K. So since you're integrating overall momentum, and also I had 2k dot p minus p squared sitting up there, and if you substitute in for k L, this turns into 2L dot P minus 1 minus 2Z P squared. Okay, so at the end of all this work, we've got delta I is minus the integral from 0 to 1 dz, 1 minus z, integral d4L over 2 pi to the 4th. The numerator was 2L dot P minus 1 minus z, 2z, P squared. The denominator was L squared minus A squared plus I epsilon cubed. Okay, so we're making progress. Actually, there's an easy step that we can do right now that's very easy. Since the denominator is just a function of L squared, and we're integrating over all L, this first integral vanishes. The integral that's linear in L vanishes because it cancels positive and negative L's. It's an odd function being integrated over a even region. So that piece drops out, and all we have left over then is this last piece, the P squared. And so we have this as integral 0 to 1, so I can pull the P squared out in front, that's easy. Integral 0 to 1 dz, 1 minus z, 1 minus 2z times an integral that's left over is integral d4L over 2 pi to the 4th, 1 over L squared minus A squared plus I epsilon cubed. Okay. So the integral that we have left over, this integral, let me just rewrite it here on the next page. 1 over L squared minus A squared plus I epsilon cubed. Well, that's certainly much easier than what we started with. But we still have some work to do just to even do that guy. The reason this is tough is there's a pole sitting here. It's not completely obvious, but we're integrating over all L. L squared is L0 squared minus L vector squared minus A squared. So that denominator there has a pole, has raised to the 3rd power. We have to somehow do that. So our next task is calculate this guy. This task comes with the next phrase. So step 1 is Feynman parameterization. Step 2 is complete the square. Step 3 goes by the name of Wick rotate. Okay? And the idea here is that because we have this difference in sign there, we can't go to nice spherical coordinates. You'd think you might try spherical coordinates here, but there's a difference between the L0 and L vector piece that doesn't let us do that. And the Wick rotate trick is going to be using complex variable techniques to turn this integral into one where we can use spherical coordinates. So it's basically going to be the following. It's going to be, we're going to let L0 equals IL4, and then this denominator will turn into minus L4 squared minus L squared minus A squared plus epsilon. Okay, which now this guy can be used with 4D spherical coordinates, which we'll do that too. But first we have to make this change such that our physics is unchanged. And so how do we do this? Okay, here's where the I epsilon comes in. Okay, so rotating is, you'll see the picture where it's a rotation. First, we want to see where the poles are in this plane. So if we look at the plane, this is going to be real L0, and this is the imaginary L0. So it's complex L0 plane. We're trying to find two contours, two paths that give the same result. Okay? And the poles in this expression here are at L0 is square root of L vector squared plus M squared minus I epsilon. That gives you one pole, and the other pole is at minus the square root plus I epsilon. Okay, if you take those and plug it into that, you get 0. So our poles in this complex plane live when L0 is real L0 is positive, it's slightly below the real axis, and when it's negative, they live slightly above the real axis. Okay, so, but now we're going to use complex variable techniques to take the integral that we have. The integral that we have is this one that goes along the real axis there, and change it into a different integral. The different integral is going to be the following. We're going to, make a contour that goes like this. It goes up like this, dot, 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 dot. It goes out to infinity, of course. Comes up here, and then comes down the imaginary axis, comes around, and comes back this way. Okay, we've chosen that so there's no poles inside that. So if I take that as my path, the integral dL0 of any of this function of L0, with the one we have to do here, is equal to 0. And so that the integral along the real axis is equal to the integral along the imaginary axis. This tells us then that the integral from minus infinity to infinity of dL0, f of L0, if I define L0 is IL4, is then I times the integral of minus infinity to infinity dL4 of this function IL4. Okay, so this is the rotation. We've taken the integral along the real axis and rotated it to live along the imaginary axis. And then this integral is going to be easier to do. So we'll define our Euclidean momentum, LE, as L1, L2, L3, L4, and we've now transformed the problem into this J3 that I had there, integral d4L over 2 pi to the fourth, 1 over L squared minus A squared plus I epsilon into, well, there's I dL Euclidean to the fourth, 2 pi to the fourth, 1 over L Euclidean squared plus A squared minus I epsilon cubed. Because it was cubed, there's an overall minus sign that gets cubed, that pulls out in front. So there's our problem now. Okay, now we have to do this one now. So we've now gotten a little better. We no longer have any poles there. And in fact, the I epsilon has done its job. We can put epsilon goes to 0 at this stage because there's no longer any poles in this thing. This is, everything's positive, definite along, well, actually, I shouldn't say that. It's not quite true. I'll keep it along. We actually have one more integral to do, and depending on the sign of A, it makes a difference. So actually, let's keep it carried along. But I epsilon has done its major job, which is telling us how to do the Wick rotation there. So that's the next step. And the last step is to do the 4D integral. Okay. And here we have to introduce 4D Euclidean coordinates. So integral d4LE is integral 0 to infinity LE, the magnitude cubed. Okay, so that's the magnitude. So instead of L squared, like R squared dr, it's L cubed dl. And then there's a bunch of angles. I'm not going to derive this. This is, you take it on faith. It's pretty easy, straight math. Here's the usual stuff that we have. Sine theta d theta. D phi goes 0 to 2 pi. The theta angle goes from 0 to pi. And if you make a sphere in a four-dimensional space, so it's a generalization of this, it goes 0 to pi. Sine squared of some angle, let's call it chi, d chi. That's the general one. Actually, the higher generalizations are sine cubed, sine fourth, etc. If you go up to get higher dimensions. But anyhow, this is spherically symmetric, so this turns into just 2 pi squared integral 0 to infinity L Euclidean cubed dLE. So we've done the spherical integral. Then our integral that we have to do is turned into minus I. We have that over 2 pi squared over 2 pi to the fourth, integral from 0 to infinity, L, let's drop the E at this stage for notational convenience, L cubed dL over L squared plus A squared minus I epsilon cubed. Okay, well that's an easy integral to do. Finally we have something easy to do. It won't last long, but this has been done. Minus I over 32 pi squared a squared minus I epsilon. So we've done that integral, and overall now we have delta I of p squared is minus I over 32 pi squared. There's the factor of p squared, the integral 0 to 1 dz. We have another integral to do, 1 minus z, 1 minus 2z over m squared minus z, 1 minus z, p squared minus I epsilon. Oh, okay, so we're almost there. We've done the most painful integral, and now we're down to just the normal integral. Okay, so there's the normal integral. At this stage, you have to then do the last integral. And this is again always at the last step in the path. Over the Feynman parameters. Okay, here I don't have there's no great technique to do this in general. These are just normal integrals. There's no more specialized techniques. I use, for this, Dradstein and Rizek. This table of integral series and products. That's the most useful reference I have. These are relatively straightforward integrals, but except that you see that integral still has a pole there if p squared is big enough. If z1 minus z integrated from 0 to 1 has a maximum of a quarter. So if p squared is bigger than 4m squared, then you actually have another pole there. And you have to do it very carefully. I should warn you that this is a case where mathematics is not good. Mathematics will give you an answer here, but it may be the wrong answer because it doesn't know how to treat this I epsilon. You have to watch out for that. Let me just quote you the answers for this at this stage, but it's just a regular integral at this stage. So delta I of p squared. Well, if p squared is less than 0, there's no poles, it's well defined. So it's minus I over 32 pi squared turns into 2 plus 4m squared minus p squared over magnitude of p squared to the 1/2 log of log square root of 4m squared minus p squared minus magnitude of p over 4m squared minus p squared plus magnitude of p. So that's the answer if p squared is less than 0. Okay. If p squared is between 0 and 4m squared, so p squared is positive but less than 4m squared, then there's also no pole. The answer turns into minus I over 32 pi squared 2 minus 2 square root of 4m squared minus p squared over p squared. Those are all positive now. 1/2 inverse tangent of p squared over 4m squared minus p squared root. Okay, that's that case. And finally, you have to be especially careful if p squared is bigger than 4m squared. It turns into the following: minus I over 32 pi squared 2 plus p squared minus 4m squared over p squared 1/2. Log again. Now it's p minus p squared minus 4m squared 1/2 p plus p squared minus 4m squared. And now there's an imaginary part, I pi. Okay, so what can you say? Wow, that's a pretty serious calculation. Pretty complicated result. This is the simplest calculation, loop calculation you can do. So this is why theorists stay in business doing one loop calculations. They're not necessarily that easy to do. But we've shown you the pathway through. You always go through this Feynman parameterize, complete the square, Wick rotate, do the integral in this 4D Euclidean, and then have a Feynman parameterization integral over it. Those are all the same things. This then completes the one loop calculation of the scattering amplitude. These p squareds are substituted in. They're either p squared is s, which is p1 plus p2 squared, or it's t, p1 minus p3 squared, or it's u, p1 minus p4 squared. Now, in the physical region, s is positive and bigger than 4m squared, so you use the last form. T and u are negative, so in the physical region, you use the first and the last expressions in the scattering amplitude. Okay, let me stop there. Again, we'll take questions on this and talk later on some more about doing loop integrals